Okay, we have a few examples left to finish, and I told you guys I'd make a video for you, so this is it. I want to continue with example 8, which says that three charges are placed at the corner of a square whose sides all have a 30 centimeter length as shown. And unfortunately, there's a little bit of a boo-boo. There is no picture shown, but the idea is not that hard to understand. I've got a charge here, and a charge here, and a charge there, and those are three corners of a square. And I can call this one Q1, Q2, Q3, however I want to do it, like that. And I know the fourth opposite corner of the square is got no charge in it. And it's at that empty point in space where there's no charge that I want to calculate the electric field. This is different from Coulomb's law, where say I've got three charges and I want to find the force on Q1 from Q3 and Q2. And I have K Q1 Q2 over R squared and K Q1 Q3 over R squared, and I have to calculate those magnitudes. For the electric field, we have only the charge of interest in an empty point in space. With Coulomb's law, I've got two charges and they are having a force directly on them. So I need the force to be K Q3 times Q2 divided by the distance between them squared. That's for Coulomb's law, finding the force directly. This is for the electric field, where I want to find the electric field due to each of these three charges. Now, the way that we work electric field problems with point charges is just like we work Coulomb's law problems with point charges. Now, this example is just a little bit off because not only is it missing a picture, it's missing the values of the charges. Whoops. So let me give you the value of the charges and we will proceed from there. So let's say that Q1 is going to be positive 8 microcoulombs. Q2 is going to be negative 5 microcoulombs. And let's let Q3 be negative 4 microcoulombs. And we're going to assume 3 sig figs. So this is really 8.00. This one's really 8.00. This one's really negative 5.00, etc. And so what's the first step in these problems? Regardless of whether it's a Coulomb's problem or an electric field problem, the first step I told you is to find the directions of all the vectors. And if it's a Coulomb's law problem, we're finding the directions of all the force vectors. In an electric field problem, we find the directions of all the electric field vectors. And we know the electric field vector has a direction that's along the way a positive test charge would feel a force. So let's find the direction of the electric field caused by Q1. And so we have Q1 here. It's going to create an electric field at this empty point in space. What's its direction? Well, we know that if we draw a line between the two, the electric field vector is going to be along that line, and it's going to be in the direction that a positive test charge would go. And so our positive test charge would be repelled by Q1 because Q1 is positive. And so it's going to be away from Q1 along this dotted line here. So I can draw that in, and I can say that the electric field E1 is going to be in that direction. Now, what about Q2? Q2 is negative. Here's Q2, it's negative. So if I put a little positive test charge in this empty point in space, which way is it going to feel a force from Q2? It's going to be pulled upwards because opposite charges attract. And so that electric field is going to point straight up, and that would be the electric field E2. That's the electric field due to charge 2, and specifically due to charge 2 at this empty point in space here. Now you guys tell me, which way would the electric field from Q3 be? Again, Q3 is negative, and so if I put a little positive charge here, is it going to be attracted towards Q3 or pushed away from Q3? And obviously, if it's positive and this guy's negative, they're going to be attractive. So E3 is going to point this way. Now, I don't yet know what the angles are for all of these. I can see for two of them they're pretty straightforward, but for this E1 guy over here, that angle's a little tricky, and I'll show you how to get that in a minute. But we now know what the vectors look like. We know what their directions look like. And so that's part of what we want to do. And so I'm going to now draw a little free body diagram of just these three vectors, and then I'll be able to show you how to calculate the angles for the three vectors. So here's my little free body diagram, and all I've done is I've drawn these three vectors and I've put them on an XY coordinate system. Now we can see immediately that E2 points straight up along the y-axis, so it's in the positive y direction, and it will have no x component. So all I have to do is calculate the magnitude of E2, and I know 100% of it is in the y direction. Similarly, E3 is 100% in the x direction, actually the negative x direction. And so if I calculate the magnitude of E3, it's going to be pointing 100% in the negative x direction. But if I look at E1, E1 has both has components along the x direction and along the y direction. And so I can draw those in, and I can say that this guy here would look like that, and this would be E1x, and this guy here over here would be E1y. And so I have all three vectors broken up into their x and y components. Again, we know that E2 is 100% in the y, so it only has a y component. E3 is 100% in the negative x direction, so it only has an x component. And E1, this blue vector here, I can replace by an x component pointing in this direction and a y component in that direction. And all I really need is the angle, and that will let me use sine and cosine to figure out what those components are. How can I get that angle? Well, let's look at the picture up above. I know from here to here is 30 centimeters, and I know from here to here is 30 centimeters. So what's that angle going to be? It's obviously got to be 45 degrees. 45 degrees. That's terrible scratching there, but hopefully you can see that that's 45 there for that angle. What if this were different sides? Well, then you'd use the arctangent to figure out what the angle is. Now, if that angle is 45 degrees, what must that angle also be? It has to be 45 degrees also. And so now I know that this angle is going to be 45 degrees, and I can use the sine of 45 and the sine of the cosine of 45 to get the x and y components. So now I have all the directions of all three electric field vectors. What do I need next? I just need the magnitudes. Let me note just one last thing though. If we look at these components, E1x and E1y, we will note that this is in the positive x direction, but E1y is actually in the negative y direction. I can see that it's pointing downward. So when I figure out what that value is, I'm going to have to make it negative, and I just wanted to point that out. So how do we calculate those electric fields? Well, if you have a point charge, the formula is that the magnitude of the electric field is KQ over R squared. And so I have my three charges and my empty point in space that I want to look at. And I already know that this distance is 30 centimeters or 0.3 meters, and that distance is 30 centimeters or 0.3 meters. And so if I think of this as a square, I know the length of that diagonal can be calculated by the Pythagorean theorem. And when you calculate that length, you get about 0.42 meters or 42 centimeters. And that would be the length of that side. And so if we want to calculate E1, we would plug 0.42 in for R, and the Q was given as being 8 microcoulombs. That's 8 times 10 to the minus 6. And so we could calculate that E1 magnitude is going to be 9.0 times 10 to the ninth. I'm going to be sloppy with my units here because I've got a limited space to write this all in on this video thing. So that would be newtons times meters squared divided by coulombs and squared. That would be the units of the K value, which is what this 9 times 10 to the ninth is. The Q that we were given was 8.0 times 10 to the minus 6 coulombs. And then the distance is 0.42 meters squared. And so when we do that, we get that the electric field is from charge 1, that's from this Q1 over here, which we were told was 8 microcoulombs. The electric field at this 42 centimeter distance away is going to be given by that. And when we do that, we get that E1 has a magnitude of about 4.1 times 10 to the fifth newtons over coulombs. And so that's what the units of electric field works out. Remember, E is F divided by Q. And if you plug in the units for K up above, the Newton meter squared per coulomb squared, and you cancel all these other things, that's what you end up with. And so that is the magnitude of the electric field from E1. And we would do the same thing. We would do exactly the same thing with the other charges. And so I would find this distance is 0.3 meters, and that's what would go into the R, and I would plug in this value of Q, which is 4 microcoulombs, and I would get an answer. And then I would do the same thing for this charge, and I know this distance is 0.3 meters, 30 centimeters, and I would plug in the charge, which we're given that charge was 5 microcoulombs, and if we do that, we'll calculate for E2 and E3 that E2 magnitude is equal to 5 times 10 to the fifth, 5.0 times 10 to the fifth, and we get that E3 is equal to 4.0 times 10 to the fifth. And so now we have our 3 vectors, our 3 electric field vectors. We know what their magnitudes are, and we know what their directions are. So now what do? Well, we have our vectors. And what I want to do next is I want to calculate these components. And so I know this guy is going to be E1 magnitude times the cosine of 45 degrees, and this guy is going to be E1 magnitude times the sine of 45 degrees, and that's going to be negative because it is in the negative direction. And I'll just make a mental note to myself that that guy's negative. So then what do? We're going to say that the total electric field is going to be E1x minus E3, and the total electric field in the y direction, oops, that's Ty, is going to be E2 minus E1x. And when you plug all of those in, you get that EX is equal to minus 1.2 times 10 to the fifth newtons per coulomb. And you get that EY, that's E total X and E total Y, are equal to, E total Y is equal to 2.2 times 10 to the fifth newtons over coulombs. And when you do that, you find that the total electric field is going to look something like this. It's going to go in the negative direction about 1.2, and then it's going to go in the positive y direction about 2.2. And I've drawn that one about twice as big as this one to give me a sense of scale. And this is going to be my E total. And I know that angle there is going to be the arctangent of ETY over ETX. And so that theta is going to be the arctangent of 2.2, the y, divided by the 1.2. And the 10 to the fifth would cancel. I'd actually have 2.2 times 10 to the fifth divided by 1.2 times 10 to the fifth. They'd cancel, and so I would get that. And when I do that, I get an angle of 61 degrees, and that would be in quadrant 2. So if I wanted this angle here, that would be 180 minus 61, or 119. And for the magnitude of the electric field, how would we get that? We would say that the magnitude is equal to the 1.2 times 10 to the fifth squared plus 2.2 times 10 to the fifth squared, all under the square root. How did I get that? That's just that squared plus that squared equals that squared. The hypotenuse is found using the Pythagorean theorem. And so when I do that, I get that the magnitude of the total electric field, E magnitude, works out to be 2.5 times 10 to the fifth newtons over coulombs. And so that works out to be my answer. It's 2.5 times 10 to the fifth newtons over coulombs. And that's basically it. Now, the next part of the problem is what would be the force on a, what was it? It was a 6 microcoulomb charge placed at that location. And we know that the force on a charge is given by simply F equals QE. And so I know what the magnitude of the electric field is. If I multiply that by 6 microcoulombs, that will give me the amount of force on that charge. And it works out to be about 1.5 newtons, something like that. So anyway, that's that problem. What are the key takeaways? The key takeaways that I want you to understand here is when you're doing Coulomb's law, we have Coulomb's law, F is equal to K Q1 Q2 over R squared. And we're calculating, I've got, a charge here and a charge there, and these guys are creating a force on them. If I'm calculating an electric field, I've got some charge, and I've got an empty point in space, and I want to find the electric field at that empty point in space. And the formula for a point charge is that its magnitude is going to be K Q over R. And so here with Coulomb's law, we have to plug in both charges into the formula to calculate the force. And then with the electric field, we have an empty space where there would be a charge. Remember, that's where we imagine our little test charges being to figure out the directions. But the steps of working these problems with point charges, whether you're talking about the Coulomb's law or whether you're talking about the electric field, the steps are the same. You find the directions, and that means find the angles of all the vectors. You find the magnitudes of the vectors using either the Coulomb's law formula or the electric field for a point charge formula, and that gives you your magnitude, and then you have a direction and you have a magnitude of a bunch of vectors, and you just add them up using vector addition. Okay, so I hope that was helpful. Let's go on to the next one. Okay, this problem says two oppositely charged parallel plates, as shown here, have a 3,000 Newton per Coulomb uniform, that is constant electric field between them, and they are 15 centimeters apart. And so we're asked to explain in words what it means to have a constant electric field. And that is simply means that the electric field has the same value, the same magnitude, and the same direction at every point in space. And so if I put a charge here, it's going to feel a force, F equals to QE. That E is not changing. And so if I put that same charge here, it's going to feel the same force. No matter where I put the charge, it's going to feel the same force because the electric field is the same everywhere. That's what it means to have a constant electric field. Remember, if these electric field lines were getting closer together, that would mean the electric field would be getting stronger. If they were getting further apart, that would mean the electric field is getting weaker. But since these lines are all parallel, they're not getting closer, they're not getting further apart, we know that the field strength is constant or uniform. It doesn't change. And how are we going to work this problem? What is the approach that we need to work this problem? Okay, there are lots of problems we're going to take this same kind of approach here. We know that the force on a charge, let me try to turn my pen on. There we go. F equals QE. And so if I know what the charge magnitude is, and I know what the strength of the electric field is, in this case it's 3,000 newtons per coulomb, I can plug that in here, and so I can say, boom, these guys are magnitudes. If I plug that 1,000 newtons per coulomb in right here, and I multiply it by the charge, what charge am I talking about? I'm talking about the charge on an electron. That will tell me what the force is. F is equal to QE. Now here's the other thing that I know. The other thing that I know is that from Newton's second law, the force is equal to also mass times the acceleration. And so I can use these equations, set them equal to one another. I know the force has to be equal to QE. That's the electric force. And if I put a charge in that electric field, it's going to feel that force, QE, and it's going to accelerate because that's what happens when you put a force on a mass. It accelerates, and we know it will accelerate according to the second law of Newton, which tells us that the force is equal to ma. So we can equate those and say that QE is equal to ma, and I can then say that the acceleration is equal to QE, and that's an absolute value bars there, divided by m. And once I have that acceleration, guess what? I can use kinematics equations because all these things are constant. The electric field is constant, the mass is constant, the charge is constant. If your acceleration is constant, then the kinematics equations apply. If I plug all of those numbers in, I'll end up with 5.3 times 10 to the 14 meters over second squared. And that's the acceleration of this guy. And then I can just simply use the second kinematics equation to work part B. We want to find out how long it will take to reach point A. Well, we know that x is equal to v naught t plus 1/2 a t squared. What is v naught? That is the initial velocity, the velocity at t equal to 0. And then what is a? That's the acceleration, and of course t is the time. Now we're told in this that the distance between the plates is 15 centimeters or 0.15 meters, so that's our x. We're going to have the thing be released from rest, so that means the initial velocity is 0. And so I can say that 0.15 meters is equal to 1/2 that acceleration that we had, which was 5.3 times 10 to the 14 meters per second squared. And then that's going to be times t squared. And if we plug in for t, we can say move everything over and take the square root, get t by itself, and we solve that, and what we find is that t works out to be about 2.4 times 10 to the minus 8 seconds. And that's how long it takes to reach the other plate, which is 15 centimeters or 0.15 meters away. Now for part B, we're asked how fast is it going? And so we can use the first kinematics equation, that v is equal to v naught plus at. And of course we can say that is 0, the initial velocity is 0. We know what the a is. We now know what the t is. And so we can plug that in and we get that the v, the velocity it has when it hits that second plate, is going to be 1.3 times 10 to the 7 meters per second. And that's that problem. Okay, last one. We have two identical metal balls which have a charge Q1 and Q2, and we're told that the force between them is 1.35 times 10 to the minus 4 newtons when they are 20 centimeters apart. So here they are. They're 20 centimeters apart, and we can say that the force is equal to K Q1 Q2 over R squared, and that's equal to 1.35 times 10 to the minus 4 newtons. That's what's given in the problem. And then what happens is they take those balls and they touch them. They bring them together. They let them be in contact. Now, what's going to happen when they're in contact? The charge is going to transfer from one ball to the other ball. And then their balls are separated and put back into this new position. And we're told that afterwards, the force is equal to 1.406 times 10 to the minus 4 newtons. And so what happens to change the force? Well, obviously the charge is redistributed among the balls. And so how much charge is now on each ball? And that's really the trick you need to understand to work this problem. Because what's going to happen is because the balls are identical, they have the same size, the charge is going to flow freely until the charges are equal. Does that make sense? Because if there's an excess of charge on one ball, the excess charges are going to be repelled and pushed to the other ball. And if too much charge gets on the other ball, it'll be pushed back, and they're just going to push the charge back and forth until they come to an equilibrium where each ball has the same amount of charge. And here's the sneaky trick. After you touch them and then put them back to their original positions, what is the charge on each ball. Let me write it down and see if it makes sense. After, each ball is going to have a charge Q, I'll call it Q star, of equal to Q1 plus Q2 over 2. The total charge is Q1 plus Q2. Each ball will get half of the total charge. And so this is going to be equal to K Q star times Q star over R squared. The K and the R is the same, but we have different charges. And I could actually just call that Q star squared if I wanted to, because Q star times Q star is Q star squared. So let me summarize over here. We've got F is equal to K Q1 Q2 over R squared, and that's equal to 1.35 times 10 to the minus 4 newtons. And we have the second equation that F is equal to K Q1 plus Q2 over 2 all squared divided by R squared, and that's equal to 1.406 times 10 to the minus 4 newtons. And so now what we have is two equations and two unknowns. And we have to solve to get the two equations and two unknowns. Now, in order to do that, we need to simplify this a bit. And so to simplify, what I'm going to do is I'm going to plug in for K in each of these equations, and then I'm going to move it to the other side. And so I'm going to plug in for R and move it to the other side. So this guy will move over here. This guy will move over there. I want to get the terms with the Q's by themselves. So I move everything else to the other side. And when I do all of that, I get that Q1 times Q2, that's this guy right here. I move everything else to the other side. That works out to be equal to 6.0 times 10 to the minus 16. 6.0 times 10 to the minus 16. And then on the other side, I get Q1 plus Q2. And that works out to be 5.0 times 10 to the minus 8. So that works out to be 5.0 times 10 to the minus 8. And up here, this would be Coulomb squared, because it's Q times Q gives me Coulomb squared. Down here, just be plain old Coulombs. And so now I have simplified this to what I can do algebra on to figure out what my values are. So I can simplify this. I've got Q1 plus Q2 is equal to 5 times 10 to the minus 8. And I'm being a little sloppy with sig figs. But that lets me write that Q1 is equal to 5 times 10 to the minus 8 minus Q2. And now I can say that Q1 times Q2 is going to be 5 times 10 to the minus 8 minus Q2 times Q2, where this guy in the brackets here is just Q1. I take my Q1, I plug it in here, so this is Q1 times, and that should be written down as Q2. So Q1 times Q2 is equal to this thing in brackets is Q1 times Q2. And what's all of that equal to? That is equal to 6.0 times 10 to the minus 16. So that's equal to 6 times 10 to the minus 16. And this is a quadratic equation. If I multiply this out, I get 5 times 10 to the minus 8 Q2 minus Q2 squared. I just took this Q2 and distributed it into the brackets, and then that's all equal to 6.0 times 10 to the minus 16, and that's a quadratic equation, and so you can plug that into the quadratic formula. And so when you plug that into the quadratic formula, you get that Q1 is equal to 20 nanocoulombs and Q2 is equal to 30 nanocoulombs. And remember, nano is 10 to the minus 9. And so that's what you get with those values when you plug them in. And so really it's just two equations and two unknowns. Okay, so we have gone through this packet and we've worked these examples. There are a few things that I just wanted to point out real quick. Not in this video, but in what we did previously, we did an example where we had to know the formula for centripetal force. And so that's something from Physics 1 that we had. And so if you remember, the formula for centripetal force was A is equal to V squared over R. And so you want to make sure that you remember these basic ideas about centripetal force and centripetal acceleration. This is, of course, the centripetal acceleration, and the centripetal force would be the mass times that. We also looked at the sum of the forces equals to 0, and we had the balls hanging from the strings, and we had to break the tension up into x and y components. And so that's basically Newton's second law. The sum of the forces is equal to ma, and in that case the A was equal to 0. Another thing we looked at was we said F is equal to ma, but ma was equal to Q times E, because the electric force is Q times E, but force is equal to ma, and so we were able to use that to calculate the acceleration. The other thing that we did was we looked at the kinematics equations. And so, you know, for constant acceleration, there's 3 important kinematics equations. If you don't remember those, you should review them. You should know those from Physics 1. And so the last thing that we did here was we did a little bit of a intuition that we had to have to figure out how the charges were on those balls. But beyond that, we did the math trick of having 2 equations and 2 unknowns. How do you solve that? You solve for one variable in one equation, and then you substitute that into the second equation to get rid of that variable. And then you reduce the number of unknown variables you have by 1, and you just keep doing that until you get down to 1 unknown with 1 equation. And then you do some algebra and Bob's your uncle. You've got your answer. You can take that answer, plug it into the previous equations, and get all your answers. All right, so I just wanted to just kind of recap that, sort of remind you of some things that we did and that you might want to review if you're a little bit rusty on them. Okay, so I hope that this video was helpful. I'm going to try to get it posted quickly, so if you have any other questions, just let me know and we'll try to get them sorted out.